Since the dawn of humanity, we have gazed at the stars and wondered, are we alone? The universe is vast, filled with billions upon billions of stars and even more planets. Is it possible that somewhere out there, another civilization is asking the same question? The search for extraterrestrial intelligence, or SETI, has captivated our imaginations for decades. Scientists have been listening to the cosmos, hoping to catch a whisper from a distant world. For years, this search has relied on traditional methods, painstakingly analyzing radio signals from space. But the universe is a noisy place, and our ability to sift through the cosmic static is limited. What if we've already received a message, a sign, a beacon from an alien civilization, but missed it amidst the cosmic cacophony? The answer to this question may lie not in bigger telescopes, but in smarter algorithms. Artificial intelligence, with its ability to process vast amounts of data and detect subtle patterns, is rapidly changing the game. AI can analyze signals far faster and more thoroughly than humans ever could. It can filter out the noise, identify anomalies, and perhaps even understand signals that our brains are not wired to comprehend. Could AI be the key to finally answering the age-old question of whether we are alone in the universe? This essay will delve into the history of SETI, the transformative potential of AI, and the tantalizing possibility that the answer we seek is already out there, waiting to be discovered. Imagine the universe as a vast orchestra, each celestial body playing its own unique tune. Stars emit radio waves, pulsars pulse with rhythmic precision, and black holes create a cosmic symphony of signals. Amidst this cosmic orchestra, SETI researchers have been searching for a different kind of sound, a signal that is not random, a signal that carries information, a signal that whispers of intelligence. For decades, the search for these signals relied on human analysis. Scientists would pore over data from radio telescopes looking for patterns that stood out from the background noise. It was a laborious and time-consuming process, akin to finding a needle in a haystack the size of a galaxy. While some intriguing signals were detected, such as the famous WOW signal in 1977, none have been definitively confirmed as alien in origin. The challenge lies in the sheer volume of data. Radio telescopes generate an overwhelming amount of information, and even the most dedicated teams of scientists can only analyze a fraction of it. Furthermore, our human perception is limited. We are prone to biases and can easily miss subtle patterns that might be obvious to a more objective observer. This is where AI comes in. AI has the potential to revolutionize the way we search for alien life. It can analyze data on a scale and with a precision that far surpasses human capabilities, opening up new avenues in our quest to find out if we are truly alone in the cosmos. Artificial intelligence is not a single entity but a collection of powerful tools that can be trained to perform specific tasks. In the context of SETI, AI algorithms can sift through mountains of radio telescope data, identifying patterns and anomalies that would be impossible for humans to detect. These algorithms learn from the data they analyze, constantly refining their ability to distinguish between natural phenomena and potentially artificial signals. Imagine an AI astronomer tirelessly scanning the heavens, its digital mind never tiring, never overlooking a single blip on the cosmic radar. This AI astronomer could analyze data in real time, identifying promising signals as they arrive. It could cross-reference these signals with other astronomical data, searching for correlations that might indicate a technological origin. The potential of AI in the search for alien life is not just theoretical. In recent years, researchers have already begun to harness the power of AI for SETI. These early experiments have yielded intriguing results, suggesting that AI might be the key to unlocking the secrets of the cosmos and finally answering humanity's most profound question. Are we alone? The journey has just begun, and the discoveries that await us may forever change our understanding of our place in the universe. The story of SETI is a testament to human curiosity, ingenuity, and perhaps a touch of cosmic loneliness. It began in earnest in 1960 with Project Ozma, a pioneering effort led by astronomer Frank Drake. Drake pointed a radio telescope at two nearby stars, Tau Ceti and Epsilon Eridani, hoping to eavesdrop on any potential alien conversations. While Project Ozma didn't detect any extraterrestrial transmissions, it marked a pivotal moment, sparking a global fascination with the search for alien life. The underlying premise was simple yet profound. If civilizations exist on other planets, they might communicate using radio waves just like we do. Radio waves are a versatile form of electromagnetic radiation that can travel vast distances through space. They are relatively easy to generate and can carry information, making them an ideal candidate for interstellar communication. SETI researchers focused on searching for radio signals that exhibited patterns or characteristics indicative of artificial origin. The early days of SETI were marked by a sense of boundless optimism and a belief that contact with an extraterrestrial civilization was just around the corner. However, as years turned into decades, the silence from the stars became deafening. The universe, it seemed, was content to keep its secrets well hidden. Amidst the silence, there were occasional blips on the radar, moments that sent shivers down the spines of SETI researchers, and reignited hope that we might not be alone. One such moment occurred on August 15, 1977, when astronomer Jerry Amon was reviewing data from the Big Ear radio telescope at Ohio State University. There, amidst the usual static, was a signal unlike anything seen before. The signal, which lasted for 72 seconds, and originated from the constellation Sagittarius, was incredibly strong and narrowband, meaning it occupied a very specific frequency range. Amon, astonished by what he saw, circled the signal on the printout and wrote, "Wow!" in the margin, a moniker that has since become synonymous with the tantalizing possibility of extraterrestrial contact. Despite numerous attempts to reobserve the WOW signal, it has never been detected again. Its origin remains a mystery to this day. Some scientists speculate that it might have been caused by a natural phenomenon, such as a comet, or a previously unknown type of stellar emission. Others maintain that its characteristics are consistent with an artificial signal, perhaps a beacon from a distant civilization. The WOW signal, whether of extraterrestrial origin or not, served as a powerful reminder that the universe is full of surprises and that our understanding of the cosmos is far from complete. It also highlighted the limitations of relying solely on human analysis in the search for faint whispers from across the interstellar void. As technology advanced, radio telescopes became more sensitive, capable of detecting fainter and more distant signals. While this increased the chances of finding something interesting, it also created a new challenge: data overload. Modern radio telescopes generate an overwhelming torrent of data, far more than human analysts could ever hope to sift through manually. Imagine trying to find a single conversation in a recording of every sound ever made on Earth. That's essentially the challenge facing SETI researchers as they grapple with the deluge of data pouring down from the sky. The task of identifying potential alien signals amidst the cosmic noise became akin to finding a needle in a haystack the size of a planet. The problem wasn't just the volume of data, but also its complexity. Radio signals from space can be affected by a myriad of factors, including interstellar dust, gravitational lensing, and the Earth's own atmosphere. Distinguishing between these natural phenomena and potential artificial signals requires sophisticated analysis and a deep understanding of astrophysics. Human analysts, despite their expertise, are simply not equipped to handle this level of complexity and data volume. The need for a new approach, one that could automate the analysis process and uncover subtle patterns hidden within the sea of signals, became increasingly apparent. The human brain is a marvel of evolution, capable of incredible feats of creativity, problem-solving, and pattern recognition. However, it is also subject to limitations, especially when faced with tasks that require processing vast amounts of data, or identifying subtle patterns in complex datasets. Our brains are wired to focus on immediate threats and rewards, a legacy of our evolutionary past. While this served us well in the jungles and savannas where our species evolved, it can be a hindrance when trying to analyze data that is abstract, complex, and seemingly unrelated to our survival. Furthermore, humans are prone to biases, both conscious and unconscious. We tend to see patterns where none exist and interpret ambiguous information in ways that confirm our pre-existing beliefs. In the context of SETI, this means that we might miss genuine alien signals simply because they don't fit our preconceived notions of what such signals should look like. The limitations of human perception and analysis became increasingly apparent as the volume and complexity of SETI data grew. It became clear that a new tool was needed, one that could analyze data objectively, without bias or fatigue, and at a scale that far surpassed human capabilities. One of the key challenges in SETI is knowing what kind of signal to look for. The electromagnetic spectrum is vast, encompassing everything from radio waves to gamma rays. Within this spectrum, there are countless possible frequencies that an alien civilization could use for communication. SETI researchers have generally focused on searching for narrowband signals, which occupy a very specific and limited range of frequencies. These signals are considered more likely to be artificial because they stand out from the natural background noise of the universe, which tends to be broadband, meaning it spans a wide range of frequencies. Think of it like tuning a radio. If you're searching for a specific station, you wouldn't leave the dial set to a random frequency. You would scan through the frequencies until you found the one that carried the station's signal. Similarly, SETI researchers scan through the electromagnetic spectrum, looking for narrowband signals that stand out from the cosmic static. However, this approach assumes that alien civilizations communicate in a similar way to us, using narrowband signals for efficient information transfer. It's entirely possible that extraterrestrial intelligence might employ communication methods that are beyond our current understanding, perhaps using broadband signals or even entirely different forms of energy. As the limitations of traditional SETI methods became increasingly apparent, a new hope emerged from the world of computer science artificial intelligence. AI, with its ability to analyze vast amounts of data, identify subtle patterns, and learn from experience, offered a powerful new tool in the search for extraterrestrial intelligence. Unlike humans, AI algorithms are not limited by fatigue, bias, or preconceived notions. They can process data 24/7, tirelessly searching for anomalies and patterns that might indicate an artificial origin. Furthermore, AI can adapt and evolve its search strategies as it learns from the data, potentially uncovering signals that would be invisible to human analysts. The application of AI to SETI is still in its early stages, but the potential is enormous. With AI as our partner in the search for cosmic companionship, we may finally be on the cusp of answering one of humanity's oldest and most profound questions: are we alone? The journey has been long and arduous, but the destination, should we reach it, promises to be nothing short of transformative. The search for extraterrestrial intelligence, with its vast data sets and subtle signals, presents challenges that traditional methods of analysis struggle to overcome. This is where artificial intelligence emerges not as a replacement for human ingenuity, but as a powerful ally, amplifying our abilities and pushing the boundaries of what's possible. Human researchers, while experts in their fields, are limited by the sheer volume and complexity of the data generated by modern radio telescopes. Our brains, evolved for survival in a terrestrial environment, are not naturally equipped to sift through the cosmic static, searching for faint whispers that might hint at intelligence light years away. AI, on the other hand, thrives in this data-rich environment. Algorithms can process information at speeds and scales unimaginable to the human mind, tirelessly analyzing terabytes of data without succumbing to fatigue or bias. They can detect subtle correlations and patterns that might easily escape human notice, revealing hidden structures within the seemingly random noise of the cosmos. This is not to say that AI is infallible or that it possesses some form of superhuman intelligence. Rather, it excels at tasks that complement human capabilities, freeing us from the limitations of our biology and allowing us to focus on the interpretation and understanding of the signals that AI helps us uncover. Section 2: Machine Learning Training the Cosmic Detectives. At the heart of AI's potential in the search for extraterrestrial intelligence lies machine learning, a branch of computer science that enables computers to learn from data without explicit programming. In the context of SETI, this means training algorithms to recognize patterns characteristic of artificial signals, distinguishing them from the natural background noise of the universe. Imagine presenting an AI with a massive dataset of radio signals, some originating from known natural sources like pulsars and quasars, others from human-made technologies like satellites and radar systems. By analyzing the characteristics of these signals, their frequency, bandwidth, polarization, and time variation, the AI can learn to differentiate between natural and artificial emissions. This training process involves feeding the AI labeled data, where each signal is tagged with its known origin. The algorithm then uses this data to build a model, a mathematical representation of the relationship between signal characteristics and their source. Once trained, this model can then be used to classify new, unlabeled signals, flagging those that exhibit characteristics consistent with artificial origin. The beauty of machine learning lies in its ability to adapt and improve over time. As the AI analyzes more data, its model becomes more refined, its ability to distinguish between natural and artificial signals becoming increasingly sophisticated. Section 3. Anomaly Detection, Finding Needles in Cosmic Haystacks. The universe is a noisy place, awash in electromagnetic radiation emanating from a multitude of celestial objects. Finding a potential alien signal amidst this cosmic cacophony is akin to finding a needle in a haystack, a task that requires not only sensitivity, but also the ability to recognize subtle anomalies that deviate from the norm. This is where AI's ability to detect anomalies comes into play. Anomaly detection algorithms excel at identifying data points that deviate significantly from the expected pattern. In the context of SETI, this could mean a signal that exhibits unusual frequency hopping, a sudden burst of energy in a narrow bandwidth, or a pattern that repeats at regular intervals. These anomalies don't necessarily prove the existence of extraterrestrial intelligence, but they serve as red flags, drawing attention to signals that warrant further investigation. Human analysts, with their expertise in astrophysics and signal processing, can then examine these flagged signals in more detail, ruling out natural explanations and assessing the likelihood of an artificial origin. AI in this sense acts as a cosmic filter, sifting through the vast sea of data and highlighting those rare and intriguing signals that deviate from the expected, those that might just hold the key to unlocking the secrets of the universe. Section 4. Signal classification, separating the artificial from the natural. Not all signals from space are created equal. Some, like the rhythmic pulses of pulsars or the radio emissions from distant galaxies, have natural origins, products of the universe's ongoing cosmic symphony. Others, like the signals from our own satellites and spacecraft, are artificial, testaments to humanity's technological prowess. Distinguishing between these two categories is crucial in the search for extraterrestrial intelligence. AI algorithms, trained on vast datasets of labeled signals, can be taught to classify signals based on their characteristics, separating the artificial from the natural with increasing accuracy. This classification task goes beyond simply identifying anomalies. It involves recognizing the subtle signatures that distinguish different types of signals, whether they be the regular bursts of a pulsar, the broadband hiss of a quasar, or the narrowband transmissions of a distant spacecraft. This ability to classify signals is essential for prioritizing follow-up observations. By focusing on signals that exhibit characteristics consistent with artificial origin, astronomers can make the most of limited telescope time, targeting those signals that hold the greatest promise of revealing the existence of extraterrestrial intelligence. AI, in this role, acts as a cosmic gatekeeper, directing our attention towards the most intriguing signals, those that stand out from the natural background noise and hint at the possibility of another intelligence reaching across the interstellar void. Section 5. Deep Learning Unveiling Hidden Structures in the Data. As the volume and complexity of SETI data continue to grow, researchers are increasingly turning to deep learning, a sophisticated form of machine learning that uses artificial neural networks with multiple layers to analyze data at unprecedented depths. These deep neural networks are inspired by the structure of the human brain, with interconnected nodes that process information in a hierarchical manner. Unlike traditional machine learning algorithms which require human engineers to manually define the features that the algorithm should consider, Deep learning algorithms can learn these features directly from the data. This ability to extract meaningful features without human intervention makes deep learning particularly well suited for analyzing complex, high-dimensional data sets like those generated by modern radio telescopes. In the context of SETI, deep learning could be used to identify subtle patterns and correlations within radio signals that might escape detection by traditional methods. For example, a deep learning algorithm might be able to recognize a complex sequence of pulses that repeats at irregular intervals, a pattern that might indicate a form of modulation used for interstellar communication. The potential of deep learning in the search for extraterrestrial intelligence is vast and largely unexplored. As these algorithms continue to evolve and as our datasets grow ever larger, deep learning may hold the key to uncovering the faint whispers of intelligence hidden within the cosmic symphony. Section 6. From Data to Discovery, AI's Role in Breakthrough Listen. The transformative potential of AI in the search for extraterrestrial intelligence is not merely theoretical. It's already being put into practice in projects like Breakthrough Listen, the most comprehensive search for alien civilizations ever undertaken. Breakthrough Listen, funded by billionaire Yuri Milner, uses some of the world's most powerful radio telescopes, including the Green Bank Telescope in West Virginia and the Parkes Telescope in Australia, to scan the skies for signs of intelligent life. The project generates an enormous amount of data, far more than human analysts could ever hope to analyze manually. This is where AI plays a crucial role. Breakthrough Listen researchers are collaborating with computer scientists and machine learning experts to develop and deploy AI algorithms that can sift through the project's vast datasets, identifying promising signals and flagging them for further investigation. These algorithms are trained on a variety of data sources, including known natural phenomena, human-made interference, and simulated alien signals. This training allows the AI to distinguish between signals of interest and background noise, narrowing down the search and focusing attention on the most intriguing candidates. The use of AI in Breakthrough Listen is a testament to the growing synergy between astronomy and computer science. By combining the power of cutting-edge telescopes with the analytical capabilities of AI, we are entering a new era in the search for extraterrestrial intelligence, an era where data-driven discoveries may finally reveal whether we are alone in the cosmos. Section 7. The Promise and the Perils. AI as our cosmic companion. The application of AI to the search for extraterrestrial intelligence is still in its infancy, but the potential benefits are vast. AI has the power to revolutionize the way we listen to the cosmos, enabling us to analyze data at unprecedented scales and depths, uncovering subtle patterns and anomalies that might otherwise escape our notice. However, as with any powerful technology, there are also potential risks and challenges associated with the use of AI in SETI. One concern is that AI algorithms might be biased towards finding signals that resemble those we ourselves produce, potentially blinding us to other forms of intelligence that might communicate in ways we haven't yet imagined. Another challenge is ensuring that AI systems are robust and reliable, capable of distinguishing between genuine signals of interest and false positives caused by instrumental artifacts or natural phenomena. The last thing we want is to mistake a stray radio wave from a distant quasar for a message from an alien civilization. Despite these challenges, the potential rewards of using AI to search for extraterrestrial intelligence are too great to ignore. With careful planning, thoughtful design, and ongoing collaboration between astronomers, computer scientists, and ethicists, we can harness the power of AI to enhance our search for cosmic companionship, increasing our chances of finally answering one of humanity's oldest and most profound questions: are we alone? Imagine the universe as an ocean of data, each ripple and wave carrying information about distant stars, galaxies, and perhaps even signs of life beyond Earth. Our telescopes, like cosmic buoys bobbing on this vast expanse, capture a fraction of this data, converting the faint whispers of the cosmos into terabytes of digital information. Yet this data deluge presents a challenge as daunting as it is exciting. How do we make sense of this cosmic symphony, sifting through the noise to find the faint melodies that might indicate intelligent life? This is where artificial intelligence steps in, not as a passive observer, but as a voracious consumer of information, a digital explorer capable of navigating the vast datasets generated by modern astronomy. AI thrives in this data-rich environment, its algorithms designed to ingest, process, and analyze information at a scale and speed that dwarfs human capabilities. Think of it as a cosmic librarian, meticulously cataloging and cross-referencing every celestial whisper captured by our telescopes. But unlike a human researcher, who might spend years poring over a single dataset, an AI can analyze vast archives of astronomical data in a fraction of the time. It can cross-reference observations from different telescopes, comparing data across wavelengths and timescales, searching for subtle correlations that might have escaped human notice. This ability to connect the cosmic dots, to find patterns hidden within the seemingly random noise of the universe, is what makes AI such a powerful tool in the search for extraterrestrial intelligence. However, simply feeding AI with data is not enough. Just as a detective needs more than just fingerprints to solve a case, an AI needs guidance, a framework for understanding what constitutes a meaningful signal amidst the cosmic clutter. This is where the crucial element of training comes in, shaping the AI's perception and guiding its search for the extraordinary. The universe speaks in a language of patterns. The rhythmic pulses of a pulsar, the swirling clouds of gas in a nebula, the faint afterglow of the Big Bang, all follow predictable laws of physics, creating patterns that astronomers have learned to recognize and understand. But what if, amidst these familiar patterns, there exist others, subtle and enigmatic, that hint at the presence of intelligence beyond Earth? This is where AI's ability to recognize patterns becomes crucial. Just as a musician can distinguish between a symphony and random noise, an AI trained on astronomical data can learn to differentiate between the natural rhythms of the cosmos and the potentially artificial signals of a distant civilization. This is not simply a matter of finding needles in haystacks, it's about recognizing the glint of a needle in a haystack full of other shiny but ultimately mundane objects. To achieve this, AI algorithms are trained on massive data sets of both natural and artificial signals. They learn to identify the telltale characteristics of pulsars, quasars, and other celestial objects, building a cosmic fingerprint database against which to compare new observations. At the same time, they're exposed to simulated alien signals, artificial patterns designed to mimic the kinds of transmissions that a technologically advanced civilization might produce. This training process is akin to teaching a language to a child. By immersing the AI in a rich tapestry of cosmic sounds, we help it develop an ear for the unusual, the unexpected, the potentially artificial. And just as a child's language skills improve with practice, so too does the AI's ability to recognize patterns become more refined with each new dataset it analyzes. The true power of AI lies not just in its ability to process information, but also in its capacity to learn and adapt. Unlike traditional computer programs, which follow a fixed set of instructions, machine learning algorithms can modify their own behavior based on the data they analyze, constantly refining their ability to recognize patterns, make predictions, and even discover new phenomena. In the context of SETI, this means that AI has the potential to become a more effective cosmic detective over time, its skills honed by experience and its search strategies evolving alongside our understanding of the universe. One of the most promising avenues of machine learning for SETI is unsupervised learning, a type of algorithm that can identify patterns in data without being explicitly told what to look for. Imagine setting an AI loose on a vast data set of radio signals without any prior knowledge of pulsars, quasars, or even the concept of artificial intelligence. By analyzing the data for recurring patterns, correlations, and anomalies, the AI might uncover hidden structures and relationships that would have eluded human analysts. This is not science fiction, but an active area of research. Scientists are developing unsupervised learning algorithms that can sift through astronomical data, identifying clusters of signals with similar characteristics, flagging anomalies that deviate from the norm, and even discovering new types of celestial objects that don't fit our existing classifications. In a sense, these AI algorithms are not just tools for analyzing data, They are becoming collaborators in the scientific process, helping us to see the universe with fresh eyes and to ask new questions about the nature of reality. This collaborative aspect of AI is crucial. While AI can analyze data at a scale and speed that far surpasses human capabilities, it is ultimately our responsibility to interpret the results, to separate the truly significant from the statistically spurious, and to ensure that the search for extraterrestrial intelligence is conducted with both rigor and a sense of wonder. Section 4. The Black Box Problem: Understanding AI's Intuition. As AI systems become more complex, their internal workings can become increasingly opaque, even to the scientists and engineers who design them. This is often referred to as the black box problem. We can see the data that goes into an AI and the results that come out, but the decision-making process that happens in between can be difficult to decipher. This lack of transparency can be unsettling, especially when dealing with something as profound as the search for extraterrestrial intelligence. If an AI flags a signal as potentially artificial, how can we be sure it's not simply a glitch in the algorithm or a reflection of biases in the training data? Addressing the black box problem is crucial for building trust in AI systems and ensuring that their insights are used responsibly. One approach is to develop explainable AI or XAI algorithms that can provide human understandable justifications for their decisions. Imagine an AI that could not only flag a signal as potentially artificial, but also highlight the specific characteristics of the signal that led it to that conclusion. This would allow scientists to scrutinize the AI's reasoning, to identify potential biases or errors, and to ultimately make more informed decisions about how to follow up on promising signals. Another approach is to combine AI with other analytical techniques, such as statistical modeling and signal processing, to create a more robust and transparent analysis pipeline. By cross-validating the results of different methods, scientists can gain greater confidence in the conclusions drawn from AI systems. The black box problem is not insurmountable, but it requires ongoing research and collaboration between computer scientists, astronomers, and ethicists. By developing AI systems that are not just powerful but also transparent and accountable, we can ensure that the search for extraterrestrial intelligence is guided by both scientific rigor and a deep respect for the unknown. Section 5. Beyond the Horizon: Pushing the Limits of AI Astronomy. AI is revolutionizing our quest for extraterrestrial intelligence, enhancing our senses and expanding our horizons. Imagine AI-powered telescopes autonomously scanning the skies, identifying targets in real time. AI algorithms can analyze data from multiple telescopes simultaneously, creating a dynamic view of the cosmos. AI could also design future SETI experiments by simulating alien signals and optimizing telescope designs. The journey ahead is filled with challenges and immense possibilities. By embracing AI and working collaboratively, we can explore the cosmos with open minds. We seek not just signals from the stars, but a deeper understanding of our place in the universe. The power of AI is pushing the boundaries of what's possible in astronomy. The future of AI in astronomy is transformative and full of potential. Section 1. 8 Signals of Interest: A New Lead in the Cosmic Quest. In 2021, researchers from the University of Toronto identified 8 significant signals using AI. These signals, found in data from the Green Bank telescope, marked a pivotal moment in the search for extraterrestrial intelligence. While not confirmed as evidence of alien civilizations, the signals exhibited unique characteristics. They were faint, fleeting whispers amidst cosmic noise, easily overlooked by traditional methods. The AI algorithm distinguished between cosmic background radiation and potential technological origins. Acting as a cosmic filter, AI identified rare anomalies that might hold the key to profound questions. The discovery injected optimism and excitement into the SETI community. AI demonstrated its potential as a collaborator in the scientific process. The signals hinted at the possibility of another intelligence reaching across the interstellar void. The transformative potential of AI in SETI is undeniable. One key characteristic of the 8 AI-identified signals was their narrowband nature. Unlike broadband emissions, these signals were concentrated within a specific portion of the electromagnetic spectrum. This aligns with how a technologically advanced civilization might communicate across interstellar distances. Imagine signaling a friend across a crowded room using a flashlight in a specific pattern. Similarly, a civilization might concentrate their signal's energy into a narrow band of frequencies. This focused beam would stand out against the background noise of the cosmos. Using a narrow band allows for more efficient transmission of information. The narrowband characteristic piqued the interest of SETI researchers. It suggested that these signals were potentially deliberate transmissions. The signals were not random bursts of cosmic energy. They were carefully crafted to carry information across the vast gulf of space. The 8 AI-identified signals were non-repeating, adding to their mystery. Unlike pulsars or radio broadcasts, these signals appeared only once in the data. This lack of repetition made it challenging to rule out alternative explanations. One possibility is that these signals were instrumental artifacts or glitches. Researchers took great care to eliminate such possibilities. Another possibility is that these signals were caused by unknown natural phenomena. The universe is full of surprises, and these signals might represent new astrophysical objects. However, their characteristics suggested artificial transmissions. The non-repeating nature added intrigue and complexity to the signals. We might be glimpsing a dynamic cosmos with fleeting intelligent signals. The 8 AI-identified signals originated from specific stars with potential for life. This targeted nature suggested the signals might be directed at our solar system. The stars were nearby and similar in size and temperature to our Sun. Stars like our Sun are prime candidates for hosting habitable planets. The discovery made these stars high-priority targets for future observations. Astronomers will search for subtle wobbles and transits indicating orbiting planets. Finding planets in the habitable zone would strengthen the case for artificial signals. We might be eavesdropping on a galactic conversation. The signals could reveal another intelligence sharing our universe. The 8 AI-identified signals remain unconfirmed as evidence of extraterrestrial intelligence. Rigorous verification is essential, and astronomers approach these signals with skepticism. Follow-up observations will confirm the signal's existence and gather more data. Researchers will look for signs of repetition and modulation in the signals. The search for extraterrestrial intelligence is a marathon, not a sprint. Even if these signals have natural explanations, the quest continues. Each new discovery brings us closer to understanding our place in the universe. The spirit of exploration drives us to seek answers to the biggest questions. The search for extraterrestrial intelligence embodies this spirit of curiosity and wonder. The search for extraterrestrial intelligence has long been limited by the vastness of the cosmos. Traditionally, SETI researchers analyze data long after observations were made. This approach is like searching for a needle in a haystack after the haystack has been scattered. By the time a potential signal is identified, the opportunity to gather more data might be gone. Powerful new telescopes and AI advancements are ushering in real-time astronomy. AI algorithms can scan the heavens in real time, identifying potential signals as they arrive. This real-time capability revolutionizes the search for extraterrestrial intelligence. AI systems act as our eyes on the cosmos, constantly vigilant and analyzing. Projects like Breakthrough Listen are incorporating AI into their data analysis pipelines. AI algorithms are becoming more sophisticated, enabling ambitious real-time SETI initiatives. The future of AI in SETI is pushing the boundaries of what's possible. We are closer to answering the age-old question of whether we are alone. The search for extraterrestrial intelligence is a numbers game. The more stars and planets we observe, the greater our chances of finding evidence of a civilization. Missions like Kepler and TESS have expanded our knowledge of exoplanets. We now know of thousands of exoplanets ranging from gas giants to rocky worlds. This exoplanet data provides a valuable roadmap for SETI researchers. Analyzing this data and correlating it with telescope observations is a daunting task. AI can cross-reference exoplanet data with live telescope data in real time. AI can flag high-priority targets for further investigation. This cross-checking of datasets increases our chances of finding techno-signatures. AI's true potential lies in connecting different realms of astronomical knowledge. Combining big data with targeted observation brings us closer to finding evidence of extraterrestrial intelligence. The universe operates on its own timescale, indifferent to human limitations. The cosmos continues to hum with activity, a symphony of celestial sounds. To detect alien signals, we need to be listening all the time. Constant vigilance is a major challenge for SETI. Telescope time is precious and researchers need to sleep. AI-powered SETI can create a system that never sleeps. AI algorithms on dedicated systems can monitor the skies 24/7. This constant vigilance increases our chances of detecting a signal. The next great discovery might occur at any moment, whether we are prepared or not. Imagine for a moment that we do receive a signal from an extraterrestrial civilization. The excitement, the sense of wonder, would be immeasurable. But then would come the hard part, understanding it. Alien minds, shaped by different evolutionary histories and environments, might perceive and process information in ways that are fundamentally different from our own. Their languages, their modes of communication, could be as alien to us as our own languages would be to an ant colony. This is where artificial intelligence might prove to be not just a tool for detection, but also a Rosetta Stone for deciphering the unknown. AI algorithms, particularly those based on deep learning and natural language processing, have made remarkable strides in recent years in understanding and translating human languages. These same techniques, adapted and refined, might hold the key to unlocking the secrets of alien communication. Imagine an AI system trained on a vast corpus of human languages, as well as on datasets of complex mathematical and scientific concepts. This AI, exposed to an alien signal, might be able to identify patterns, structures, and even underlying concepts that would elude human analysts. It might be able to recognize mathematical constants, physical laws, or even philosophical ideas encoded within the signal, providing us with a glimpse into the minds of a truly alien intelligence. The challenge of decoding alien communication is immense, perhaps even insurmountable, but with the help of AI, with its ability to learn, adapt, and see patterns that elude human perception, we might just be able to bridge the gulf between our minds and those of a civilization from another world, opening up a dialogue that could forever change our understanding of our place in the cosmos. The search for extraterrestrial intelligence is more than just a scientific endeavor. It's a reflection of our deepest curiosities, our longing to know if we are alone in the vast expanse of the cosmos. For decades we relied on our own limited senses, straining to hear a whisper amidst the cosmic roar. But now, we have a new ally in this grand pursuit: artificial intelligence. AI is more than just a powerful tool, it's a transformative force that's changing the very way we explore the universe. It can analyze data at scales and speeds unimaginable to the human brain, detecting subtle patterns and anomalies that might easily escape our notice. It can connect the dots between different observations, correlating data from telescopes across the globe, and even guiding those telescopes in real time to investigate promising signals. But AI's potential goes beyond mere analysis. As our AI systems become more sophisticated, they might one day be able to decipher the language of the cosmos, translating the whispers of a distant civilization into something we can understand. They might help us to bridge the gulf between our minds and those of beings shaped by entirely different evolutionary paths, opening up a dialogue that could forever change our understanding of our place in the universe. The journey ahead is filled with challenges, but also with immense possibilities. With AI as our partner in exploration, we are entering a new era in the search for extraterrestrial intelligence, an era where data-driven discoveries may finally reveal the answer to one of humanity's oldest and most profound questions. Are we alone? Even if we never receive a confirmed signal from an alien civilization, the search itself is a testament to the human spirit. It speaks to our innate curiosity, our drive to explore the unknown, and our enduring hope that somewhere out there, amid the billions upon billions of stars, There exists another world where life has taken hold, where intelligence has blossomed, and where beings gaze up at their own night sky, wondering if they too are alone. The universe is a vast and mysterious place full of wonders we have yet to comprehend. Every new discovery, every new observation, brings us one step closer to unraveling its secrets. And while the search for extraterrestrial intelligence remains a daunting challenge, it is a challenge we embrace with both humility and a sense of awe. For in the end, whether we find evidence of alien civilizations or not, the journey itself will have transformed us. It will have pushed the boundaries of our knowledge, expanded our horizons, and challenged us to confront the profound implications of our own existence in a cosmos far grander and more mysterious than we ever imagined. The universe is a silent symphony, a symphony of light and energy, of creation and destruction, playing out across billions of years and trillions of miles. We may never know all its secrets, but with the help of AI, we can listen more closely, more attentively, and perhaps one day we might just hear a familiar melody, a whisper in the cosmic wind that tells us we are not alone.